This video and exercise 1025 are meant to help you predict the products of ozonolysis on an alkyne. So if you have a carbohydrin, or a hydrocarbon, if you have a hydrocarbon, that's a molecule just made of hydrogen and carbon, with a triple bond in it, that's an alkyne. And what do you get when you treat that alkyne first with ozone? That's O3. And if you're using alkynes, you'll remember, you might remember from alkenes, the second step was a reducing agent like DMS, dimethyl sulfide. But for alkynes, the reducing agent is just going to be water. It's less expensive and less toxic, and also easier to work with. So it ends up working with the ozonolysis of alkynes, and so that's the second step here, using that water. Now the ultimate effect of this is that it breaks the triple bond in half. You can sort of break it in half and think of these two pieces, the piece on the left and the piece on the right. So let me redraw both parts of this molecule but separately. First I'm going to draw the piece on the left, and I'll even draw the triple bond. And then I'm going to redraw the piece on the right. Sure, I can include the triple bond if I want. Just, I just don't want to draw them together, so I'm separating them. Okay, so now what do we do? Well, now you turn the ends of those carbon skeletons, you turn the ends of those carbon skeletons into carboxylic acids. I'm going to draw those in a slightly different color. I'll draw those in purple here. Get rid of the pi bonds, and on that carbon on the end, draw and here, get rid of the pi bonds. On that carbon on the end, draw a double bond to oxygen and a single bond to an OH. Now that's a carboxylic acid. A carboxylic acid is carbon double bonded to oxygen, and that same carbon single bonded to an OH. That whole group of atoms is its own functional group. It always behaves the same way, no matter what carbon chain it appears on. And the name for that is a carbox. So carb, you have the carbon, ox, you have the oxygen, and then ilic acid, so carboxylic acid. This hydrogen here ends up being acidic. It can leave the molecule. So if you have that, the H plus can leave the molecule because the electrons that are left behind are lilic to the pi bond, and so they can be spread out through resonance and stabilized that way. So the hydrogen here on this OH is acidic, and that's why it's called an acid. So that functional group is called a carboxylic acid, and that will come up a lot in the future. Carboxylic acids are responsible for the word acid in amino acids. They give that amino acid name to that molecule. Amino acids have carboxylic acids in them. So they're a unique molecule, and you get them when you do this ozonolysis on an alkyne. So we've done one half. Let's do the other molecule. If we get rid of that triple bond, and then we just draw a double bond to an oxygen and a single bond to an OH onto the carbon that was involved in the triple bond. And so that's it. Those are your two products. You'll notice that this on the left gets turned into this, and this on the right gets turned into this. So when you're trying to predict the products of the ozonolysis of an alkyne, draw a sort of squiggly line through the triple bond, separate the two sides into two separate carbon chains, and where the triple bond was, add carboxylic acids. Now that's if the alkyne is internal, if it's not at the end of a carbon chain. We'll talk about what happens if it's terminal at the end of a carbon chain when that comes up. So that's A. Let's try it with another molecule, B. And here we are, a terminal alkyne. We see that this triple bond is at the end of the carbon chain. So the question is, what would happen if you treated this first with ozone and then in a separate step with water? And watch out for these steps. Make sure you always write the number for the step if they have numbers, because you don't want to mix them all together. They'll react with each other instead of the carbon compound. So if they have numbers, that's a very important part of the recipe. Okay, well, ozonolysis breaks apart the triple bond. Let's start with the two pieces. So we'd have sort of this one carbon at the very end, then we'd have these 1, 2, 3, 4 carbons over here. So that's what we get if we break apart that alkyne. Just drawing the two pieces separately. Okay, the piece on the right will look familiar. We erase the triple bond and we draw in the carboxylic acid. Double bond to oxygen, single bond to OH. So that's the product that we get from that chain. But if you have a terminal alkyne, if you ever have this one lonely carbon at the end of the chain that gets sawed off, that turns into carbon dioxide. So if you think of this reaction as adding bonds to oxygen, here you have 3 bonds to oxygen. Carbon dioxide is really just 4 bonds to oxygen. And so that's what this one lonely carbon turns into. It ends up turning into carbon dioxide. That only happens if you have a terminal alkyne, an alkyne at the end of a carbon chain. You'll get the carboxylic acid for the part that has a carbon at the other end, but if there's ever a carbon all by itself, it turns into carbon dioxide. Okay, let's try another one. So here we see an alkyne, a triple bond between carbons, and the question is, what will happen to this if we bubble ozone through here and follow it up with a water wash? So that's ozonolysis, and you'd want to break apart the triple bond and redraw those two pieces separately. So you'd have the sort of carbons over here. There's where your triple bond was. You had a triple bond, and then that carbon is bonded to a 5-membered ring on the other side. So if you sort of compare with the thing above, these are just the molecules we have above, but separated from each other. Okay, so then what you do is get rid of the triple bond and turn those into carboxylic acid. So double bond to oxygen, single bond to OH. Get rid of the triple bond and turn the carbon that was involved in it into a carboxylic acid. So double bond to oxygen, single bond to OH. And those are your 2 products. Those are your 2 products. When you do ozonolysis of an alkyne, you get carboxylic acids. Remember that if you do ozonolysis for an alkene, you either get a ketone or an aldehyde. So make sure those are separate in your mind. Compare this with the videos that we made before in the previous chapter for ozonolysis of alkenes. Let's try one last one. So we see a triple bond, we see an alkyne. What would happen if you bubbled first ozone through that alkyne, and then you followed that up with a water wash? That's ozonolysis. Ozonolysis breaks apart the triple bond. So that triple bond would break. And here, you might remember from the previous chapter the unique thing about ozone, because it's breaking a sigma bond in addition to the pi bonds. You can break rings open and turn them into straight chains. So the first thing I want to do is to draw this as a straight chain. And I think the easiest way to do that is to number the carbons. So if I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 carbons, I can draw those out in a straight chain. So first 1, 2, 3, 4, 5, 6, 7, 8, 9. Oops. Let's do that one more time, sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's a lot of carbons. So then I can number these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And I numbered them left to right. You could have numbered them right to left. It'll leave you with the same molecule. The thing to notice is that the triple bond was on carbon number 1 and carbon number 11. So I'll redraw that in just as a sort of reference point. So I had a sort of triple bond here, and I had a sort of triple bond here on carbons number 1 and 11. You can see that those broke apart and left us with a straight chain. Well, when you do ozonolysis on an alkyne, a hydrocarbon that has a triple bond, get rid of the triple bond, make sure you still have the same number of carbons, and just draw a double bond to an oxygen, single bond to an OH, a carboxylic acid. Get rid of the triple bond without getting rid of the carbon, Just don't draw the triple bond and have a double bond to an oxygen, single bond to an OH. So a carboxylic acid. And so this is really the product that you would get here if you took this cycloalkyne, that alkyne, that hydrocarbon with a triple bond going in a ring, and you bubbled ozone through it, O3, and followed it up with a water wash. So hopefully this video gives you a sense, of how you can, not so much of the mechanism, but just how you can predict what product you'll get in synthesis. If you do ozonolysis, O3 followed by water, in 2 separate steps with an alkyne.